Good. We have a lot of stuff to cover. Actually, I should have spent more than 1 hour, or we have 50 minutes. And yeah, Ole, as Siri said, from University of Oslo, been in this game for quite some time, but I'm not a computer scientist. I have a training in chemistry. So there's a lot of things, and if you feel that you need more time, the sessions are recorded and the slides are available because there's a lot of stuff to cover. So without further ado, we set on. Right. So best practices, I've tested it and it works. Of course, you can always do it better, but things are, what I'm presenting is things that I have tested and I know working, but it should always be possible to make it better. So, key question, especially when you are not if you develop yourself, this is not that relevant because you should actually know whether or not you're writing a program in parallel or not. But understanding what you run on the system is a key factor. So you get some random executable from somewhere, and who knows what you are running. But you are not alone. There are people, there are staff, there are paid staff to help you. Yeah, and remember that from yesterday also, then do not abuse the resources. So what information do I need? And how do I get this data? I mean, I have a random executable that I download from internet. First of all, that could be quite dangerous. It could do things that you wouldn't actually want it to do. But if you know that this executable is safe, you can run. Do I run in parallel or not? Are they executable independent, or yeah, or is it massive amount of using independent executable, an array run? We'll have a little bit about that, because there was somebody yesterday who said that they are not running in parallel. They are running a massive amount of bash scripts. If you can partition your problem into a massive amount of bash scripts, you are actually very good, because it can scale to infinity if they are independent. So that's a very nice way of doing jobs in parallel. It's not really high performance computing, because they have always been about running a single program in the fastest possible way. But high volume production is something, and the systems that we have are set aside for Betsy, for the real HPC, but Saga is more like high volume. So you can easily run jobs of a single thread on Saga, but run multiple of them. And you don't have to be a rocket scientist to understand that if you launch a huge amount of single-threaded jobs that do a lot of I/O, each single one, it will overwhelm the I/O system. That's happen. When that happens, it could take 2 minutes to do an LS, which is not very nice. But of course, we cannot spend all the money on the I/O system to accommodate for that. So if the I/O system is sluggish, it feels like cold oil, it is because people are running a lot of jobs that do overwhelm the I/O system. So that's a fact of life. This is something things are, but it do affect the interactive performance. So 2 minutes to then LS is we regard as unacceptable, but it happens from time to time. So gathering data about my work. Application, single core, multi-core, shared memory, distributed memory. It's a lot of keywords, and we'll go through them step by step and figure out what's happening. Remember that we now have a random executable. We don't really know whether or not they are single core, multi-core, shared memory, distributed memory. This is something that we can clear up now. Most important, memory footprint, cores, processor, they are two words of the same thing. And of course, I could spend my whole session about scaling. I tried to convey some scaling yesterday. Scaling is the most important thing, because it's so easy to abuse the resources by not taking care of scaling. Input and output are key elements. As I said, 2 minutes to do an LS on Saga is unacceptable, but it happened when you do a lot of I/O. And of course, runtime is another metric, because one thing is that you get accounted for runtime, but it's also things that there are maximum runtimes on the system. Could be week, 2 weeks, a month, but it's set up by the sysadmin, and it can change from time to time. So the maximum runtime is an issue. So single node application, single or multi-core shared memory. I mean that shared memory means that there is a single memory image, also implies that we are confined to a single machine or a single node, single host, whatever you like to call it. There is a machine, a self-standing machine, which has memory and one or more processors to run your jobs using data in that memory. Keywords are open. If you know that they're about the application, the keywords to look out for is OpenMP, multi-core, shared memory, threaded, pthread, POSIX thread, and NCPU. If you get to some of these keywords, you know that you have a multi-core system using shared memory. And there are some tricks down below here, LDD and such, that might help you along. Those you should just record and play with and see what you get out of them when you are running. So that's the message to take home, those 4 lines, LDD and strings. Nice small utilities to use to check what your program contains. If you do strings, there's a lot of interesting things you can dig out from there. So if we have distributed memory, single or multi-core, the keywords to look out for is MPI, message passing interface, and distributed memory. And we covered yesterday that distributed memory also means that every executable are independent of any other executable. The only way they deal with each other is that they are using MPI, so they can send messages from one executable to another. So the only thing the executable know is my rank and the total number of ranks. And of course, there is a communicator that you can talk to each other, but that time it's something that's hidden behind the scenes. So again, two things, LDD and strings again, to look for MPI. Running applications. Memory. How much memory do we need? How many cores do we need? And the runtime. And how do I set and request that? It's not easy to know. You read the manual. You can ask other users. You can guess. Just pick a random number. And trial and error. It's actually the best because you learn along the way. You might discover something that you didn't look for, and you found that, wow, that's a good thing. That I will remember for the rest of my life. So by testing and doing trial and error, it could be quite good. But again, you are not paid for playing around with computer science when you try to do biology. So if you could get the answers either from other users or other, you're better off doing that, or contact us. We can help you along. Explore parameter space. Yes, that's a nice one, but it's very time consuming. Running the HPL test when you are trying to get the optimum performance for the top 500 list of the fastest computers in the world, we run for days because some of these minor parameters can have an impact on performance. 1 or 2% more get you higher on the list. So we explore a lot of parameter space, but it's very time consuming. So this is a special case, the simplest case at all. This is typically high volume production. This doesn't require any parallel programming at all. Yet again, it is the best possible way of doing parallel programming, because you see that executable, you put I have a bash script here, a Slurm script, and execute a command or executable, and I've just done some DD, copy some files, randomly numbers, and that's a single threaded job. And you launch it with the commands on the right hand side there, and that number 3 could be a very large one, and that will actually run X copies of your executable, but of course you have to give it some different inputs, either random inputs if it's Monte Carlo or special inputs. That piece you have to deal with yourself. But any of the executables are independent of all the others, so it will scale linearly. The performance you get or the amount of work you get done scales linearly. So this is a very, very nice thing if you have a lot of tasks that are trivial and simple and single-threaded. Just launch them with the array and you can run as many as you like. Okay, interactively, in order to check that your input is working and compile. Well, no, we are not dealing with compiling in now because we have an executable. How do I run my executable? What kind of parameters? How does it actually work? Then you can run test on the front end. You are not allowed to run production on the front end. Not 5 to 15 minutes wall time on the execute on the front end is quite okay. But if you use a significant amount of memory on the front end, you should request a compute node instead, reserve a node using Slurm, and then run interactively and explore. So anything that you will have a feel for this yourself. If you're using a significant amount of resources on the front end, you shouldn't. But small amount is okay. Some systems also have interactive nodes when it's okay to use half the node or even the whole node and run interactively for hours or even overnight. That's why the nodes are called interactive. But we don't have a large pool of those, so that's only for some other systems like Fox on UIO has interactive nodes. They have a lot of memory, a lot of scratch, and so on. Running the application to get to know what's actually going on behind the scenes, since this is unknown if it's a random application you run. You log into the application, the node where the application is running, and there are two nice tools that you can run. It's top and HTOP. HTOP is shown here on the right hand side, where you can see all the cores here. There are 64 cores on the system, and you can see which one of them that are allocated. Well, of course, I'm not alone on this system, so you see, but you can see how much memory it's used, and you see the green one is actually in use, and the yellow one is cached and so on, and you can see that the swap has been used. So HTOP can give you a lot of information, and top gives you another information about overview. There was also a question about yesterday about the memory, about the IO performance. If you see the status where it all says R here, on the green line, you see S for status. If that one is D for disk weight, then something is wrong. If it stays constantly in D, something is wrong. Then maybe you should file a ticket and ask if there's something we can help you with. This one is an interesting, because we talked about running two threads on a single core. This is the example where we are running two instruction streams, a blue instruction stream and a yellow instruction stream. This processor can run two instruction streams in parallel. And you see they don't overlap. They have their own pathway through the system the whole way. So the blue one uses the floating point things. The yellow one uses the integer one, and they run in parallel because they are not sharing any executable units. Imagine now that we put the yellow on top of the blue. They will share floating point rename. They will share the multiple or addition or multiple or add. They will share these executable units. Of course, they have two multiple and two add, but they will share the register file and they will share the scheduler. So they will not run at full speed. So generally, they will compete for the resources. So that's why running two identical instruction streams on the same core is a very bad idea. To run two different instruction streams on a single core is okay. But since MPI programs contain the exact same executable, all of them, for most cases, then they will compete for the resources, and that will impede performance. So you're better off running only a single instruction stream per core. There's a lot of things to be said, but that could be the theme of a whole seminar. So how do we run parallel applications? We have this now figured out that we have a distributed one, distributed memory. Since we are requesting 2 nodes, this is typical one, or if you have more than 1 node, of course, this is distributed memory, MPI. And we can set how many tasks we want to run per node. In this case, 4, gives us total of 8 ranks in total. There is 1 CPU per task, so there's only 1 thread per MPI rank, and time and memory. Time and memory you have to figure out yourself. Well, all of them you actually have to do. So there's a 5-dimensional space. So only educated guesses are possible. You can't run through all of them. Then, what do we get out when the job has finished? It's more interesting. You see that it took 4 minutes about. Not that bad. And since we are running on 4 CPUs, then it will be elapsed time was only 1 minute. So elapsed is equal to wall time. Only 1 minute. So we know that if we set 5 minutes wall time, it will be okay. And there is the memory statistics. And you can convert that to megabyte and so on, or gigabyte or whatever it is in K in this example. This is the maximum resident memory. So you need to specify your memory, your memory slightly bigger than this. But this is, Slurm now gives you the maximum resident memory. So if you rely on this number, increase a little bit, you should be okay. I said should, I can't guarantee, because there are some corner cases when this fails a little bit. So for a short while you might be over, and it escapes Slurm's ever-watching eye. But C group doesn't sleep in class, so C group might kill you anyway. And so if you get that one, you have to increase it a little bit. We'll cover that one about the auto memory later on. Input and output. There are no tool that we have ready at hand that can show whether or not your pattern is random or sequential. But what we do have is the maximum disk read and written. In this case, it's about 1 gigabyte of data. So that one we can dig out. How much data did you write and how much data did you read? So this one is okay. So you know, yeah, but it doesn't say whether or not it's random or sequential. Unfortunately, we are looking into that. As I mentioned yesterday about the storage, and you see if you are using the NVMe RAM, it's tremendous. This is for Fox at Oslo, but some Saga has also SSD or NVMe on some of them on the compute nodes. So you get a tremendous speed up, especially for random access. For sequential, it's not that bad, because the disks can, if you have a lot of disks, you can easily get good bandwidth. But if you have random, then you have to move the read head to the special place of the disk, and that's a mechanical process, and it takes a long time. Hence, the blue random read is close to 0. Then there is what kind of access you are doing. And we see that for most cases, and the message to take home is cached memory, cached disk access, which is the default. So if you don't know anything, don't do anything. Don't think that memory max synchronous and direct is a good idea. Cache normally beats the performance wise. Then we have parallel file system performance. Of course, all the file system except the local ones on the national system are global parallel file systems. And by using more processes in parallel, you get higher performance up until a certain limit when it doesn't get any better. So you see at 32 processes, we get quite good performance. You get the best performance. If you do more, it slows down. But it could also be that this is a system under load. So yeah, the general message to take home is that if you could split the IO into more processes, you get more done. So this one I can't go through. This one you have to print out and review in your spare time to think what's going on. So without further ado, please copy this down and keep it as a reference. And then where do I keep my files? Avoid copying large file. If you have some input files residing on project area or other places, and you are only going to read it once, you can just as well read it from your program and not staging it to the work area, because it's only going to be read once. And if you read it by copy or read it from your program, it's just the same amount, and you save space on the work area. But if you do a lot of read and write, then of course it has to reside on the working area. The scratch area has this benefit that when your job finish, everything is cleared, so you don't have to clean up yourself. Scaling, there is nothing more important than scaling. Please check scaling. Do not run at 1,000 core on the green line here. We discussed this something yesterday. Now there is some scaling theory ahead, so you might feel that this is ants on the Möbius tape. So speed up. I think we don't have time to go through this, but of course this is the gloomy one. This is Amdahl's law. It says that you cannot increase the speed too much by running in parallel. But the next one is Gustafsson's law. It means that you can speed up because you do more work, and then the parallel part will become bigger and bigger and bigger. So those two slides you can read and think what's happening when you increase the parallel time. What I normally do is to set the parallel execution time to 0 and see what's happening. This is a plot compared like yesterday, where we plot the NPV benchmark. This is one of them, the multi-grid. And here is clearly demonstrating what I said yesterday, that the MPI scales better than the OpenMP. OpenMP generally scales okay to a smaller amount, but MPI tend to scale better. And it could be that the system, that the input data is too small with a larger footprint. Again, Gustafsson's law, if you increase the footprint, you of course following Gustafsson's law, you do more work, it scales better. So again, check scaling. This is like the example yesterday. And of course, you can run hybrid jobs when you are combining the two, when you have multiple threads per rank, which is also quite common. There's an exercise. Unfortunately, we don't have time to go through the exercise, but do you remember the exercise from yesterday? Feel free to play around and do the scaling test, which brings us over for the last 20 minutes to troubleshooting. So it doesn't work. You're desperate. Keep calm. Think. And when all goes wrong, where do I start? Of course, we would like to end up on the green one with no problem. Can you blame somebody else is my favorite. Where do I actually start? Okay. This is something that it doesn't start. What do I do? Does it find the libraries? Can it run? We do an LDD on A.out, and you have to load the correct modules to do this test, so that you launch the same modules or load the same modules interactively, and you issue this command. You see that there are 4 files that is not found. A lot of missing files like this tend to be that there is a missing module. But which module? And you can use find. You can see that the find command will actually give you a long path to the 2021 Fortran compiler. Aha. Then you run module spider Intel compilers, and then you'll see that there are 2 Intel compilers that could be used. Try one of those, and you see that there's a 21.4, which is the same thing as the find suggested. So you could try launching one of those, launching that or loading that module, and you should be okay. Next one, there is some, how do I start the application? Is it an MPI application? You do the LDD trick again. You see that there is a library called libMPI, found at Cluster Software OpenMPI, and you run the spider again, looking for versions, and you see that there are several versions, and you can try one of those. The point is that the SO40, if you want to find the correct module, you have to do more checking to see which one of them that contains, use the find again to see which module contain the libMPI SO shared object .40. So there is some testing needed to figure this out. Then you get illegal instruction. And this is a bad one, because this is that there are different instructions set on the different processors. While they are almost compatible, there are small incompatible things in the system. And while the AMD compilers contain AVX2 instruction, the AMD processor have the AVX2 instructions, the Intel compiler put in test to check whether or not it's an Intel processor, and it fails. So this one is coming from the Intel compiler saying that that it's not an Intel processor and complains. There are ways of dealing with it. You can read the documentation about building. So does Slurm, now we managed to start our application. So now does Slurm start your job? So we know established that we can run the executable, but Slurm doesn't want to start. So if you go back, you see there are several things that could go wrong: association limit, resource limit, time limit, etc., etc. So job submission failed. It could be that the account is not right, the project name is not right, it violates the number of nodes, tasks, etc., time limits. So Slurm, try to emit sensible error messages and read those carefully. Try again, read the new errors, review the manual pages or the documentation pages, and see if you can figure something out there. When you've done this a couple of iterations and it still doesn't work, you can file a ticket. Billing limits. This is an interesting one because there is no more compute time left, or that you have jobs in the queue that will eat up all your quota, and you can run the cost command to see how much is there. And core hours are calculated from number of cores you asked times the wall time. And if you specify a very, very long wall time and a high core count, you multiply those together and you get a very, very large number. If that very, very large number is bigger than your quota, it doesn't matter if your job is only running for 2 minutes. If you say that it will run for 120 hours, it will only be accounted for 1 minute after it's run. But before it runs, Slurm will think that you will run for 120 hours. Hence, it won't start because there is no more quota for that one. So you get accounted for only what you run, but to start, Slurm needs to know that you have enough hours wall time multiplied with number of cores. This is cost command. Yep. So you see here, we ask for 181 tasks and 162 hours, and that number is 13,122, which is clearly more than 1,000. So this is how you can see if you are overrunning your quota before starting. So specified missing name and combination and so on, misspelling project name, quota, or account name is easy to do, but you have to check the spelling and read the emitted error messages carefully. It's very often a mistake. I mean, the NN numbering system is easy to have a different digit there, and then it won't run. And the violating accounting, quality of service possibility. And of course, there are a number of nodes, of course, are outside the limits, too few or too many. On Betsy, you are not allowed to run below a certain limit. On Saga, there is a limit of how many you can run, so there are some limitations on the number of cores or number of nodes you can ask for. Wrong quality of service, I mean, if you are in some kind of development queue or something, and you specify too long run times, etc., it will be wrong. And if wall time setting too long, there are limits on how long the wall time could be. If that number changes time to time, so you better look that up in the documentation. Again, Slurm tried to give you help. If everything fails, file a ticket. So time limit is set too long. Normally 1 week is the maximum. So you have to be sure that you are not setting it too long. 7 days, but it could be, sometimes it's longer, sometimes it's shorter, but it's generally a week. So it's 7 days. And the syntax for 7 days is 7 and dash. The other ones have colons. So it's either 168 hours, 0 minutes, 0 seconds, or 7 days, 0, 0, 0. So your job got submitted, but failed to start. Priority, resource dependency, reservation. Ask Slurm. You see, it's in PD pending on priority. Note down the job ID and ask Slurm for details and brace yourself for impact. This is what you get. So you just have to start, read carefully. First is the user ID, priority. You see that you are priority 19,000, blah, blah, blah. Its job state is now actually running. And you can go down to runtime. It's been running for 1 second. Time limit is 5 minutes. And the submit time, and when it could have started, and then the accure time, which I don't really use. I mostly look at eligible time. When can it start? If that one is far into the future, then you probably ask for too many resources, or the runtime is too long or something. So you just, if you don't understand what's going on here and don't really know what all these strange words mean, look up on the Slurm documentation. They will explain in detail all these strange numbers. But this is the way of getting hold of what's going on behind the scenes. And It's an insight of how Slurm do things inside there. Back to the simple list. Priority. Jobs with higher priority are waiting for compute nodes. Resources. A job is waiting for compute node to become available. Dependency. A dependency is set to wait for other jobs to finish. Reservation. The job is waiting its advanced reservation to become available. Association limit. The job association has reached its maximum job count. And this is the resource limit. Job has reached some resource limit. Again, you have to read some in the manual. Man-SPatch might give you a help, but you will also need sometimes to refer to the documentation from Slurm, which is available on the net. So the job failed. Again, it tried to emit sensible messages. They programmed quite a lot to get this. There are some out and there are some error files, unless you redirect them yourself to some other files. They must be scrutinized before submitting a ticket and read the manual. Few errors escape logging to the Slurm log files. So this one is a simple one. You reach your time limit because the system is 1 week. Your own or the system's 1 week. So then you either have to run it, set your wall time higher, or if it's more than 1 week, you try to use it slower, or in special cases, if you have a very, very good reason, you might get an extension if you ask for it. But I can't guarantee that the sysadmin on duty will grant that. But you can try if it's really needed. Then it's an interesting one. The out-of-memory troll is let loose. So you overstepped your memory limit. Either your own or the C group were triggering this. And your job is promptly crashed. It's just killed. C group will just kill your job if you run out of the memory limit. The out-of-memory troll is even worse. It can, if you get that on your own computer, it can start killing off things it shouldn't. So be careful not to run out of memory. This one is my favorite because you launch your job and nothing happened. There is no messages, no nothing. Your job is just dead. And if you don't try to make a new file, you won't really know that your disk quota is overrun. So it's a catch-22 situation. You don't know what's going on, but the system cannot give you any messages because it cannot write to any file because your quota is overrun. So you don't get any errors logged. This is one of these special cases when there is nothing. So if your Slurm job crashes and there is no logs, nothing, try to make a new file, try to create a new file with a few bytes. You will easily see that if you say Emacs banana, that's a very nice way of dealing with files that you know for sure is junk, calling them by fruits. So they can easily be deleted. When you cannot delete this file, if it's called banana, yes, you can. So try to make a new file called banana with a few bytes. As soon as you try to save it, you will see that your disk quota is exceeded. Then you know what to do. You have to delete files or move or whatever. But the quota is checked only every 10 minutes, so it's easy to run over the quota. I managed to overrun the quota quite heavily here because I start writing commands and writing from dev 0, which is quite fast, and I set the block count to very high. No, the count to very high. And when the Slurm exits, it's killed by disk quota enforcement. Then it cannot write because the quota is heavily overrun. You can check the quota with D usage, and you can easily see that you overspend your quota. So this is the times when there is no help from Slurm. So I managed to finish ahead of time. I had to go very fast, and there was no time to stop and discuss the subject. But yeah, this is unfortunately the way things are. There are recordings, and you can have the slide for review later on. And of course, after you thought and read some of the documentation, don't hesitate to file a ticket.